Extrema on an interval. Extrema is the plural for extremum. So these are Latin words. And basically it means max values, min values. The plural of that, so it's either extreme, either the maximum or the minimum. Those are extreme values. And for those, minimum, maximum are the singular. Plural is maxima, minima. We're just going to say min and max. But just so you know, that's the appropriate vocabulary. The extreme value theorem says if f, which I need an f there, is continuous on a closed interval, I, so that's what we're calling the interval. So it's going from A to B. It includes the endpoints. That's why it's closed. Closed means it includes those endpoints. Doesn't go on forever. Then f has both a minimum and a maximum value on the interval. Right? So if I draw some nice continuous curve and it starts at A and it stops at B, somewhere in that curve I'm going to have the maximum y value and a minimum y value. So in this case, the maximum occurred at the endpoint B, and the minimum occurred, well, on this one it's at 0, but it's not at an endpoint. Okay, so the technical definition of this is that if C is some point in that interval from A to B, then f of C, meaning the y value that goes with C, is the absolute minimum on the interval if that y value is less than any other y value in the interval. Obvious, right? And if it's larger or greater than any other y value on the interval, then it's the maximum. On an open interval, meaning we're going from negative infinity to infinity, meaning my graph has arrows to show that it's continuing, then I'm not necessarily going to get an absolute max or an absolute minimum. But I can get what we call a relative max or a local max. They both mean the same thing. Different vocabulary, depends on the textbook you're using. Okay, so if I look at this first graph here, I would be able to say that that right there is a relative maximum. Relative to the points to the left and the right of it, it is the largest y value. Locally, it is the largest y value. Is it absolutely the largest y value? No, because this function's continuing up to infinity. So it's a relative maximum. Down here, we have a relative or a local min. Relative to what's to the left and the right of it, it's the lowest y value. It's not absolutely the lowest y value because we are continuing our y values down to negative infinity. But locally, or relative to what's to the left and the right of it, it's a minimum. This graph here is an absolute value. The maximum, we're not going to have one, right? To the left and the right, it's going off to positive infinity on both sides. So there is no relative or absolute max. But this vertex of it here, we're going to call a relative minimum. And it also, on this graph, I know by looking at the graph, it also happens to be the absolute minimum, right? It is the lowest value on my graph. Okay, so we're going to discuss how do we find the absolute maxes and mins. To find them, we need to find critical points or numbers depending on the textbook you use. Some textbooks say critical points, some say critical numbers. Critical numbers give us those possible relative maxes and mins. They occur when our derivative equals 0. Now think about that. That means our slope of our tangent line is 0. That makes a horizontal tangent line. So I have that here and here. And those give me maxes and mins, right? Or when it's undefined. Well, over here, my tangent line is vertical, and we know a vertical line has a slope that is undefined. That's a critical point, but it doesn't happen to be a max or a min. I also have a max here at that cusp, at that corner, that sharp point. But what do we know about taking a derivative? Can I take a derivative at a sharp corner? No. So at that point, f is not differentiable. But yet, it's a critical point, and it gives me a local max. Okay, and then I have this point at D here where my derivative is 0. I have a horizontal tangent line, but again, I don't get a max or a min. So we get all these critical points that don't necessarily result in maxes and mins. So they might be nothing, but they might also be relative maxes or mins. So we have to find them, and then we check. We find them by taking the derivative, setting it equal to 0. If it happens to be a rational function, then we look for when is it undefined or when is its denominator equal to 0. So let's look at that. So if I want to find extrema, my maxes and my mins, on a closed interval, remember that involves endpoints, and we saw on the first graph one of the endpoints was the absolute max. First, we want to find the critical points inside A and B. So not including the endpoints, because we're going to check those later. But inside, where are the critical points? Then we want to evaluate the function at the critical points. We want to find the y values that go with them. Then I'm going to find the y values, or evaluate the function, at the endpoints. Then I look at my y values and I determine which one's the highest, which one's the lowest. That's going to give me the absolute max, the absolute min. Okay, so let's look at an example. F of x equals 3x to the 4th minus 4x cubed on the interval going from -1 to 2. Now, I graphed it on my graphing calculator to see what it looks like. I'm pretty sure that that right there is going to be my absolute max. That right there is going to be my absolute min. But let's do it using calculus. So first we're going to find the critical points. To do that, I need the derivative. So f prime is going to be what? Derivative of 3x to the 4th is 12x cubed and minus 12x squared. So we said critical points occur when my derivative equals 0 or is undefined. Well, I don't have a denominator, so I can't divide by 0, but I can set this polynomial equal to 0. So we'll say 0 equals. Now, if I'm going to find the zeros, I need to factor my polynomial. What is the greatest common factor I can pull out of both of these terms? So I'm going to pull out a 12x squared, and that's going to leave me with x minus 1. So my critical numbers or critical points are going to be x equals 0 from setting that equal to 0, and x equals 1 from setting that factor equal to 0. Okay, well, I see those on my graph. There's x equals 0, and there's x equals 1. X equals 0, is that a max or a min, a relative max or a min? No, it's nothing. But without the graph, I wouldn't know that. So what we do is we're going to evaluate our original function at the critical points. That's the next step. So f of 0 equals, well, if I plug a 0 in here, 3 times 0 minus 4 times 0 is 0. If I evaluate it at 1, I'm going to get 3 minus 4 is negative 1. And then we're told to evaluate at the endpoints, right? Because we've already seen from looking at the graph, the endpoint's going to give us the absolute max. So if I evaluate at negative 1, we're going to get 3 plus 4, because negative 1 cubed is negative. Negative times a negative is going to make that positive 4. So we get 7. My function evaluated at 2, well, let's see, 2 to the 4th is 16. 16 times 3 is 48. 2 cubed is 8, and 8 times 4 is 32. So we're going to get 16. So my highest y value is here at 16, so we're going to get an absolute max at 216. My lowest y value is negative 1. So we get an absolute max, or absolute min, at 1, negative 1. Let's do another example. Okay, f of x is 2x minus 3x to the 2/3 on the interval negative 1 to 3. So I graphed it to see what I'm dealing with here. And it looks like that right there is going to be my absolute min. And then this is actually, it's hard to see on this graph, but this is actually going to the point 0, 0, which is higher than this 3, negative 1. So that's going to be my absolute max. So I'm looking at that just to make sure that our results come out correct when I do it mathematically. I also see that I'm going to have a relative min somewhere right in there, because relative to what's around it, that's a minimum value. But I'm not going to classify that. We're not ready to do that yet. We're only ready to do absolute extrema. So let's follow the procedure for this. If I take the derivative, I get 2 for the derivative 2x. For 3x to the 2/3, a 2/3 comes out front. And we get x to the negative 1/3. Well, 3 divided by 3 goes to 1. So this is just 2 minus 2x to the negative 1/3. Now, here's where we're starting to use those answers that were simplified up till now whenever we look at an answer key. In solving for my critical points, I need to see a numerator and see a denominator. Because remember, we're looking for what makes the derivative equal 0. Well, that's when the numerator equals 0. What makes it undefined? That's when the denominator equals 0. So I told you way back when, there is a purpose to rewriting our answers when we find derivatives, and now is when we're getting to that. So I'm going to rewrite this. I'm going to factor out the 2 and say it's 1 minus x to the negative 1/3, which is the same thing as 2 times 1 minus 1 over x to the 1/3. And if I multiply my 1 by x to the 1/3 over x to the 1/3, I can get a common denominator, right? And so this will become 2 times x to the 1/3 minus 1 all over x to the 1/3. So to find my critical points, or my critical numbers, I'm going to have to set the numerator equal to 0, set my denominator equal to 0. All right, so for the first one, if I add 1 to both sides, I get x to the 1/3 equals 1. If I want to get rid of the 1/3 exponent, I need to cube both sides because that's a cube root, right? Well, if I cube 1, I just get 1. So we have a critical point at x equals 1. And then x to the 1/3 equals 0, cube both sides, we're going to get x equals 0. So now we need to evaluate our function at 0 and 1, and then negative 1 and 3. Okay, so I rewrote the function and the 4 values I need to evaluate it at so we could see it on this slide. And if I evaluate the function at 0, which is one of my critical points, we're going to get 0. If I evaluate it at 1, we're going to get 2 minus 3 equals negative 1. If I evaluate it at negative 1, now let's think about this. I get 2 times negative 1 minus 3. And I'm going to separate this 2/3 into, this is negative 1 squared. And then I take a cube root of it. So I square the negative 1, it's going to become positive 1. Then I take a cube root, I'm just going to get 1. So this is negative 2 minus 3 is negative 5. And of course, you could always just type that in your calculator as negative 1, as long as it's in parentheses, raised to the 2/3 power. For 3, I'm going to get 2 times 3 minus 3 times the cube root of 3 squared, which is 6 minus 3 times the cube root of 9. Okay. It's not a perfect cube. I can't simplify it by hand. If I need to figure out what this value is relative to the other y values, we got to make that a decimal. That's the only way I'm going to know where it stands compared to the other y values. So if I calculate that as a decimal, I get approximately negative 0.24. So we're looking for our highest and our lowest y values. Well, negative 5 is going to be my lowest, so that's going to give me an absolute min at negative 1, negative 5. My highest is going to be 0, and that's going to give me an absolute max at 0, 0. So let's go back and look at our graph. That's what we saw. Absolute max was at 0, 0. Absolute min was at the end point. And at our other two values, yeah, I got a relative min along the way, but the only reason I know what it is right now is because I looked at the graph. And then we got another end point.